स्टार्ट केलं का थेरम आधी? So we continue. Proof. Since H is complete and Y is closed. So Y is complete by the theorem that subspace of a complete matrix space is complete if and only if it is closed. We have seen this theorem in previous notes. If H is any complete matrix space and Y is its subspace, then Y will be complete if and only if it is closed. And we have given Y be any closed subspace of Hilbert space capital H, that is, it is complete as a metric space metric induced by the inner product. As Y is closed, Y is complete. Since Y is convex, we have the theorem that we have seen, theorem of minimizing vector, and the next theorem that we have seen now, that delta is equal to norm of x minus y. Such y exists, it is unique. And in next theorem we have seen that z is equal to x minus y is orthogonal to y. For every small x belongs to capital H, there is y belongs to capital Y such that x is equal to y plus z. Z belongs to capital Z is equal to y complement. By the two theorems that we have seen now. Because Z is equal to x minus y. And Z is orthogonal to y. It means that Z is orthogonal to every element in y. Here Z belongs to capital Z. It is orthogonal to every element in y. It means that Z is orthogonal to set y, so that it belongs to complement of y. That is, capital Z is equal to y complement, because Z is any element in capital Z and it is orthogonal to every element in y. So that capital Z is equal to y complement by the previous theorems. We have to show that H is equal to direct sum of y and z. We have x is equal to y plus z. If H is direct sum of y and z, then for any element x in capital H, we have to represent x is equal to y plus z, where y belongs to capital Y and z belongs to capital Z. And this representation is unique. That is, x is equal to y plus z, then we do not have any other element x1 is equal to y plus z. Or we can say we do not have any other elements y1 or z1 such that x is equal to y plus z1 or x is equal to y1 plus z, or x is equal to y1 plus z1. That is, this representation should be unique. In that case, we can say that H is direct sum of y and z. By definition of direct sum, H is direct sum of y and z if every element in H represented as direct sum of element in y and element in z, where this representation should be unique. So to prove uniqueness, we assume that x is equal to y plus z1 is equal to y1 plus z1, where y comma y1 belongs to capital Y and z comma z1 belongs to capital Z. Then y minus y1 is equal to z1 minus z. Y plus z is equal to y1 plus z. Y1 take to left hand side. So y minus y1 is equal to z1 minus z. Since y minus y1 belongs to capital Y, because we have y belongs to capital Y and y1 belongs to capital Y. Y is a subspace. So by definition of vector space, y minus y1 also belongs to capital Y, closure property. And existence of inverse property. Whereas z1 minus z belongs to capital Z, which is equal to complement of y. So that y minus y1 belongs to y intersection y complement. This implies that y is equal to y1. And also z is equal to z1 because y intersection y complement is equal to 0. It is null. तुम्ही हा थेरम लिहा तुमच्या बुकमध्ये, रेग्युलर लिहत चला, रेग्युलर लेक्चर्स अटेंड करा, सो दॅट तुमच्या हातात 4 चॅप्टर्स राहतात आणि एखादा चॅप्टर टाइम टेबल आल्यानंतरही तुम्हाला करता येतो. प्रेझेंटही लावा, कालची आणि आजची. चॅटबॉक्स मध्ये आपलं नाव लिहा. जे काल प्रेझेंट होते त्यांनी ब्रॅकेटमध्ये कालची डेट, दॅट इज 14, ब्रॅकेटमध्ये 14 लिहा, 14,15. आणि जे फक्त आजच प्रेझेंट आहेत त्यांनी ब्रॅकेटमध्ये फक्त 15 लिहा. Now we read the next theorem. The title of theorem is dense set. For any subset capital M not equal to phi, for any subset capital M which is non-empty subset of a Hilbert space capital H. Huh. The span of M is dense in capital H if and only if M complement contains only one element, that is 0. We know that a subset capital M of a metric space capital X is said to be dense in capital X if closure of M is equal to capital X. Here, capital M is dense, span of capital M is dense in capital H. It means that every element of capital H is either belongs to span of M or is limit point of span of M.
Hello.
If a set M is dense in metric space capital X, then every element of capital X is either element of capital M or either limit point of capital M. So that we can say closure of M is equal to capital X, and so we say M is dense in capital X. I give you the definition of dense set to you. हे झालंय टोपोलॉजी मध्ये मागच्या सेमिस्टर. Given that for any subset M, non-empty subset M of a Hilbert space capital H, the span of M is dense in capital H. If and only if M complement is equal to set containing only 0 element. Span of M contains such elements such that every element in span of M is expressed as linear combinations of elements in M. Let proof. Let an element small x belongs to M complement. We have to show that M complement is equal to 0. It is phi. So let any subset M, non-empty subset M of Hilbert space capital H. Let span of M is dense in H. And we have to show that M complement is equal to phi. It contains only 0 element. Not equal to phi, it contains only one element, that is 0. So let an element X belongs to M complement, and assume that V is equal to span of M. V is dense in capital H, so that every element in capital H is either point of V or either limit point of V. Then X belongs to closure of V is equal to H. V bar, it indicates closure of V. V is dense in H. It means that closure of V is equal to H. So there is a sequence Xn in V such that Xn converges to X. We have written the theorem on closed set. If a set is closed, an element X belongs to a closed set, let arbitrary closed set M, then there exists a sequence Xn in M such that Xn converges to X. We have written this theorem. Since X belongs to M complement, and M complement is orthogonal to V, we have inner product of Xn comma X is equal to 0. Xn is a sequence in V. V is orthogonal to M complement, and X belongs to M complement, so that inner product of Xn comma X is equal to 0. The continuity of inner product implies that inner product of Xn comma X converges to inner product of X comma X. The theorem that we have learned yesterday on Monday. Inner product X comma X is equal to norm of X square is equal to 0, so that X is equal to 0. Since X belongs to M complement was arbitrary, this shows that M complement is equal to set of only one element, that is 0. Conversely, suppose that M complement is equal to set containing only 0 element. If X is orthogonal to V, then X is orthogonal to M. Span of M is V. We show that V is dense in capital H. M is subset of Hilbert space capital H. So that M belongs to M complement. X is orthogonal to M, so that X belongs to M complement. Orthogonal complement of M, and X is equal to 0 because orthogonal complement of M, it contains only 0 element. Hence orthogonal complement of V is equal to 0. Because X is orthogonal to V, and we have shown that X is equal to 0, so that orthogonal complement of V is equal to set containing only one element 0. Noting that V is a subspace of capital H, we thus obtain V bar is equal to capital H. With in the theorem that we have learned, y is equal to v bar. The theorem states that y is a closed subspace of a Hilbert space, then h is equal to direct sum of y and y complement. As V is a closed subspace of H and V complement is equal to set containing only zero element, so that closure of V is equal to capital H, because complement of V contains only zero element. Hence prove that V is dense in capital M, but V is equal to span of M. Hence span of M is dense in capital H. We stop here. We continue tomorrow. You can leave the meeting.